So I've got m1a plus m1g, ft equals m1a plus m1g. And the other version of f2 that I have is this guy, m2g sine theta minus m2a, ft equals m2g sine theta minus m1a. Let me just check and make sure I did that right. m2g sine theta minus m2a. Good. So those two things are equal to each other. m1a plus m1g equals m2g sine theta minus m1a. Oh, did you catch that mistake? m2a, 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 not m1. Okay, good. There it is. There's the entire summary. Ft from the analysis of mass 1, Ft from the analysis of mass 2. They're equal to each other, and now I can solve for what you want, or in this case what I want, acceleration of the system. So I'll gather my terms, m1a plus m2a, that equals m2g sine theta minus m1g. Acceleration times m1 plus m2 equals g m2 sine theta minus m1. So the acceleration of the system is g m2 sine theta minus m1, all divided by m1 plus m2. There it is. The acceleration for this block on a ramp system. Let's notice a couple of things. One is that we're used to acceleration being f over m. Now notice that the numerator here, g times this quantity, that's the stuff that's going to move the system. That's the force. I've got this part which is pulling down the ramp, and this part which is pulling up the ramp. Who wins? Well, it depends on the angle and which is bigger, m2 or m1. But the point is that one of them is going to pull to the positive x side, and the other one is going to pull to the minus x side. Okay, that's fine. And that m, the inertia, the mass that's going to resist the movement of the system, that's in the denominator. And sure enough, here it is, the bulk of the system. The masses combined, those are the things that are going to resist the acceleration of the whole system. Let's look further now at what happens if we apply a couple special cases. One case is where theta equals 0, and the other special case is where theta equals 90 degrees, this is. And we'll look at that on the next page. Acceleration of the system. Uh-oh. It's not working. What happened to my pen? I'm going to pause. Oh, that's funny. It just wasn't showing up. I just restarted the app. Let's see if I can get going here. Okay, so we had acceleration equals g m2 sine theta minus m1 over m1 plus m2. And that was for this system where I've got m2 on the ramp, m1 over here. They're connected by this little cable over a pulley, and the angle here is theta. And I was saying we would try two special cases. One of them where theta equals 90, where I rotate this ramp all the way up to be vertical. And now what this looks like is Atwood's machine. I've got M1 and my tether and M2 and my pulley. If theta equals 90, sine of theta, sine of 90, that's 1. So A equals G M2 times 1, which is just M2 itself, minus M1 over M1 plus M2. And this is the rather famous and very useful Atwood's machine summary. That's the equation for Atwood's working. And that, by the way, is, again, a reference to problem 63. No, problem 34, kind of. 34 is actually a little bit more complicated, but anyway. Atwood's, like problem. What did I just say? Oh, I'm starting to lose it. Nothing new there. Problem 34. That's that case. We also have the case where theta equals 0. In other words, where I take this thing and instead of having a ramp at all, if theta equals 0, if the ramp is flat, then M2 is just sitting up on this tabletop and M1 is hanging down. And by the way, in the case of at least problem number 31, there's no friction. And so we got our pulley sticking on a stick, and the system is going to accelerate over that way, which is to say that way, downward, for sine of 0. And the sine of 0 is 0. In other words, for this A equals G, M2 sine theta minus M1 over M1 plus M2, then this whole term goes away. And we're left with acceleration equals minus M1G over M1 plus M2. And you might remember that that is the solution we got for that problem. I think it was mass A and mass B, but point being, if the tabletop is flat, if there's no pitch, if theta equals 0, then M2 isn't going to be a force that moves the system. It's not, excuse me, it's not pulling to the left, it's not pulling to the right, because it's on a horizontal surface. And yet, there's still an M2 in the denominator because its mass is present and will slow down whatever happens because M1 is pulling downward because of its weight. Okay, that's 20 minutes. That's plenty. Geez.